Hello, today we're going to go over a problem that requires the use of the steady state approximation. So in this problem, we're asked to write the rate law for the production of NO2F. We are not only given the overall reaction, but we are also given the three-step mechanism. Notice in the mechanism that there is no indication to which step is the slow step. Because there is no single step that's slower than the others, we must use the steady state approximation. This states that the concentration of the reactive intermediates remains relatively constant throughout most of the reaction. Due to the steady state approximation, we need to make a few equations to satisfy the assumption. Something to notice in this problem is that we have two reactive intermediates. Our first reactive intermediate is NO2F2. And you know that that's a reactive intermediate because you see it both being created in step 1 and consumed in step 2. And then you also have a reactive intermediate with this monatomic fluorine, which is both created and consumed in the reaction mechanism. So we'll first apply the steady state approximation to NO2F2. So the steady state approximation tells us that the concentration throughout the reaction of intermediate stays relatively constant. So another way of putting that is the instantaneous rate of change of the concentration of NO2F2 for a given time is 0, because the concentration of this reactive intermediate throughout the reaction is assumed to never change. So because the rate of change of the concentration of NO2F2 never changes, that means the rate of formation of this intermediate is equal to the rate of consumption of the intermediate. So first let's determine the rate of formation of NO2F2. So that is the instantaneous rate of formation of NO2F2 per unit time is equal to, and now if we look back at our mechanism, we have NO2F2 being produced here, and do you see it anywhere else being produced? No, right, there are no other places it's being produced, so K1 times NO2F2. So now let's find the rate of consumption of NO2F2. So if you look back at the mechanism, you'll see NO2F2 here is being consumed. So this is one step where it's being consumed. So that's K2 times the concentration of NO2F2. But you'll also notice that it's being consumed in this reverse step, the K negative one, since this is an equilibrium step. So we can just add these two rates together. That would be K negative 1, 2F2. So now that we know the rate of formation and the rate of consumption, we can apply the approximation. And because we know the concentration is staying constant, that means the rate of production and the rate of consumption are equal. So that would give us K1 times NO2 F2 is equal to K2 times NO2 F2 plus K1 negative 1 times NO2 F2. So now solving for the concentration of NO2 F2, we would get K1 times NO2 F2 divided by K2 plus K subscript negative 1. That's equal to the concentration of NO2 F2. So now I'll do the exact same thing for the monatomic fluorine intermediate. So now let's apply the steady state approximation to the reactive fluorine intermediate. So the steady state approximation again tells us that the rate of change of the concentration of monatomic fluorine at any given time throughout the reaction is 0. This allows us to make the assumption that the rate of formation is equal to the rate of consumption throughout the reaction. So first we'll determine what the rate of formation is for monatomic fluorine in this reaction. So here we see fluorine is only being produced in this second step. That tells us the rate of formation for fluorine is equal to K2 times the concentration of NO2F2. And so now we do the same for the rate of consumption of monatomic fluorine. And then again we look back to our mechanism and see that fluorine is only being consumed in this last step. So that means the rate of consumption is purely determined on that step. That's K3 times the concentration of monatomic fluorine times the concentration of NO2. So now applying the approximation, we can set these two equal to each other since the concentration throughout the reaction never changes. That's K2 times NO2F2 is equal to K3 times the concentration of F and NO2. So again, like what we did with NO2F2, we're going to solve for the concentration of monatomic fluorine and get the concentration of monatomic fluorine is equal to K2 times NO2F2 divided by K3 times NO2. So now that we have these two equations, let's write the rate law for the production of NO2F2. Because we want the rate law for the production of NO2F, and it's produced in this very last step, we're going to use the very last step as the rate law. So that is, let's move down here, the rate of production of NO2F at any given time is equal to K3 times the concentration of monatomic fluorine times the concentration of NO2. So looking back at the overall reaction we're given, you'll see that monatomic fluorine is not in the overall reaction, and it is an intermediate, so we must make sure to get rid of that monatomic fluorine. So we'll substitute this in for that, and that'll give you K3 times K2 times NO2F2 times NO2 divided by K3 NO2. You'll notice that these cancel, but we still have this NO2F2 reactive intermediate in our rate law. So again, we'll substitute this other equation we determined into NO2F2, and that'll give us K2 times K1 times NO2 times F2 divided by K2 plus K subscript -1. So now looking at this rate law, we don't see any intermediates. That tells us we've applied the steady state approximation correctly. So according to the steady state approximation, this is the rate law. So remember, the steady state approximation is the most general approach to chemical kinetics. If you don't know anything about any of the steps in the reaction, then you should use the steady state approximation to determine the rate law. Good luck and see you next time.